Hey everyone, welcome back to our channel NCERT Science, and today in this video we are going to do chapter 10 in NCERT Science for class 9, and that is gravitation. Alright, so this is a physics chapter, and before I start the explanation, I just want to go over my standard speech as always. Alright, so first thing I would like to mention is that this video is helpful for those preparing for CBSE exams, NTSE, NEET, and JEE. So for NEET and JEE, this video will serve as a good foundation recapitulation video. All right. So so it's gonna be very helpful. I hope it's going to be helpful. All right. The second thing is that I encourage you to take your own notes. All right. So I am going to be presenting in my own words, and I have pictures taken from the NCERT Science textbook that I found online on their official website, on NCERT's official website. So just as how I am presenting in my own words, I expect you to write down your notes in your own words, because that's only going to help you remember better during your exam. All right. Now the third thing is that I intend these videos to be like recap videos that you can watch very quickly, maybe a day before your exam, to just go over all the concepts, so I'm trying to go in a steady pace, but I'm trying to go a little faster. So if you feel I'm going fast, feel free to adjust your YouTube settings to 0.75 speed, so you can understand if you understand in a slower pace, no problem at all. If that's going to help you understand, by all means, set your pace to 0.75 speed. All right, so chapter 10, gravitation. All right. So, as I said before, this is a physics chapter, and I think we have two more physics chapters, but don't take my word for that. I'm just, I think. Alright, so this is all a basic introduction of sorts. Alright, so I want you to go through it and see if there's anything important in there. Alright, so starting with gravitation. So how they set up this concept is by asking us a question. So, I mean, by giving us a statement and making us relate to whatever we've been seeing almost every day, alright? So the moon goes around the earth, right? We know that. We know that the moon goes around the earth. And we also know that when an object is thrown upwards, it reaches a certain height before it falls down, right? Down to the ground or down backwards, right? So when you throw paper, when you toss it upwards, it's going to reach a certain height. If this is you, alright, and if you throw a paper upwards, it's going to go upwards, but after it goes to a certain distance, it starts traveling back again, and it hits the ground, or it hits your friend or something, right? So that's also something that we know, that when you throw an object upwards, it travels to a certain height before it retraces its path and starts moving downwards, right? So that's how Newton's famous apple story, that was the concept behind behind the apple. He realized that an apple fell to the ground, and he started thinking, what made this apple fall to the ground? And then he started experimenting on that, and then he realized that it was gravitational force, which happens to be a very important thing apparently, right? So if the earth can attract the apple, can it not attract the moon? Is the force the same in both cases? So we know that it's the apple fell to the ground because of gravitation, and Newton was thinking, if the same force that brought the apple to the ground or towards the earth acts on the moon, how come the moon is still able to stay there? Right? That's what he thought, and that's what he experimented on, and that's how this chapter came into the syllabus. Alright, so He argued that at each point of the orbit, the moon falls towards the earth instead of going off in a straight line. So it must be attracted by the earth, but we do not see the moon falling towards the earth. So he thought gradually it was going to spiral towards the earth and collide, but we know that it's not going to happen. That's not going to happen, um, right? So this is an activity here. All right. So before the thread is released, this is what we talked about. I get 8, right? So before we leave the thread, I gave you the example of a shot put player. Before the shot put player releases the metal ball, it moves in a circular path with a certain speed. All right. So at every point, it changes its direction. So if you take point A, it's traveling like this, right? If you take point B, it's traveling like this. You take point C, it's traveling like this. So at each point, if you draw a tangent, the directions of all the tangents are different. So at each point along its path, that ball or this rock here is traveling in a different direction. All right. So and the change in direction involves the change in velocity, and change in velocity is acceleration, right? So it's a change in direction at every point on the circle, right? It just keeps going like this, right? So that change in direction causes acceleration or a change in velocity. All right. So and the acceleration keeps the body moving along its circular path, and that is acting towards the center. So the force is called centrifugal force. Centrifugal force is center-seeking force, all right? And in the absence of this force, the stone flies off along a straight line, all right? So if this is the circle here, at every point is going to just fly off like that. It's not going to continue moving like this. It's going to fly off. Or if not this point, it's going to fly off at this point like this. It's not going to keep moving like this. Alright, so the force that keeps the stone or the ball revolving in its circular path is called centripetal force, and centripetal is the center seeking force. So it's at every point it makes sure that the object is getting attracted towards the center of this circle. Alright, so if that is happening, how come the object's not falling back inwards, right? So the answer to that would be another opposing force. Alright, so just like how friction is a resistive force, if this is the centripetal force, suppose this is my key of sorts, so whatever I'm doing in red is centripetal, alright, and whatever I'm doing in blue would be the opposing force, which is called centrifugal. Alright, so how you can remember the difference between centripetal and centrifugal is if you think about chemistry, a chapter, I don't remember which one it was, but we talked about the separation of different mixtures, right? If you haven't watched that video, go back to the chemistry chapter. So in that we had centrifugation, that method called centrifugation, and we learned that because of the difference in its masses, the centrifuge makes the heavier particles get accumulated towards the ends of the test tubes, right? So if we have 3 arms of the centrifuge and there were 3 test tubes there was a test tube attached to each arm, because of the fast rotation of this centrifuge, we saw that the heavier particles tended to get accumulated near the bottom of the test tube, right? So centrifuge is centrifugal force, and centrifugal force is bringing the particles towards the ends, right? So centrifugal is away from center. So if this is the center, the particles are being moved away from the center with the help of a centrifuge. And centrifuge, the spelling would be centrifuge, is just this E that's being replaced by the AL. Alright? Okay. So centrifugal force is acting away from the center, and centripetal force is acting towards the center. Alright? So this is an important difference that you're supposed to remember, because it confuses many people, and those who set the exam paper like to test this concept usually, because they know most people get confused by this topic, and so it's very important for you to remember. Alright? So the motion of the moon around the earth is due to centripetal force. So the centripetal force is provided by the force of attraction of the earth. Alright? But if there was no such force, the moon would pursue a uniform straight line motion. So if this is the earth, let me do the earth in blue. Alright? If this is the earth, that's a very bad circle, but I don't know. Let's do this. Alright? Okay. Yep. So this is the earth, and this is the moon. Right? If there was no centripetal force, if the moon was here, it would just travel along a straight line. It doesn't matter if it was this direction or this direction or this direction or even this direction, which would make the moon collide with the earth. That would happen if there was no centripetal force. But because there is a centripetal force, the moon is going to move like that. Alright? At every point, it is being attracted to the center of the earth. It is being attracted, but it's not going to fall. And why is that? Because of a resistive centrifugal force which acts away from the center. So it's like plus adding 2 and negative 2. Add 2 and negative 2. What will the answer be? 2 minus 2, which is 0, or negative 2, positive 2. They get cancelled, and that's 0, right? So opposite and opposing forces or opposing symbol signs, they cancel out to become neutral. So each centripetal force gets cancelled out by another centrifugal force, and that causes neutrality between the motion, neutrality in the motion of the moon around the earth. Alright, so according to the third law of, if a falling apple is attracted towards the earth, we do not see the earth moving towards the apple. And why is that? So according to the third law of motion, which is every action has an equal and opposite reaction, the apple does attract the earth. But according to the second law of motion, that says for a given force, acceleration is inversely proportional to the mass of the object. What's the mass of the object compared to the mass of the earth? It's very negligible. That is why the earth doesn't move towards the apple. It does move, but it's very, very, very negligible. Alright? So we do not see the earth moving towards the apple, but how come the earth is not seen moving towards the moon? Because the mass of a moon is relatively more than an apple, and it's also significant. Alright? If we're talking about celestial bodies, the mass of a moon is less than that of the earth, but it is significant. So how come the earth is not moving towards the moon? Right? In our solar system, all our planets go around the sun. So every single planet goes around the sun, and by arguing the same way, we can say that there exists a force between the sun and the planet. If there is a force between the planets and the sun, according to Newton's third law of motion, every action should have an equal and opposite reaction. So the sun also should have an equal but opposite attraction force towards every other planet, right? So Newton concluded that, so he deduced all of this from one basic truth. He began building upon those truths, and he began concluding few statements, and once he concluded enough statements, he reached this idea that not only does the earth attract an apple and the moon, but all the objects in the universe attract each other. So a pen and say the pen and the paper attract each other, their masses are so negligible that you can't see them, but they attract each other. Similarly, your pen and a pencil attract each other. Similarly, maybe your desk and your chair attract each other, right? That's how every object in this universe attracts another object. Two stars attract each other, two planets attract each other, but it depends on the mass, whether it's negligible or it's significant. That all depends upon the mass of the object. Alright, so this force of attraction between objects is called the gravitational force. Alright, so now that we understood what gravitational force is, let's see what the universal law of gravitation is. Alright, so the universal law of gravitation says that every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Alright, this is a very important law that you need to memorize. Alright, this is one of the few laws that you are supposed to memorize because it's very important. Alright, and there's not much modifying that you can do here other than just change the order of proportions. You can say every object in the universe attracts every other object with a force inversely proportional to the square of the distance between them and directly proportional to the product of their masses. But you can't change anything internally because it's a very strict law. There's not many synonyms that you can add and modify it a lot. So it's important that you memorize this law. Alright, so let's say this is object A and this is object B. Alright, so they have distance d in between them. Object A has a mass capital M. Object B has a mass small m, like uppercase m, lowercase m, and G here is the gravitational constant. Alright, so this concept about constants, let's talk about that. So in this law, we just said that the gravitational force is directly proportional to the product of their masses. So uppercase m multiplied by the lowercase m, which is the product. That is the first clause. The second clause said it is inversely proportional to the square of distance between them. So that is the second clause. When we combine 1 and 2, we know that force is proportional to uppercase m lowercase m by d square. Alright, so this is the proportionality symbol, this one here, and in order to make the proportionality symbol turn into the equality symbol, we add a proportionality constant. Alright, so that constant is a set number that makes the force that always makes the force proportional to this part right here. Alright, so you can see for any proportional equation. Alright, so we remove the proportionality symbol and add an equality symbol by adding a proportionality constant. Usually they're named based on, they're given the letter closer to their concept. Because this is gravitational force, it's given a capital G. Most of the time it's given like that, but there are a few instances where it's not exactly related to the concept, and it's usually K, the lowercase letter K that's used as a proportionality constant. But here, this is your actual formula for, let me get rid of this. Alright, so this one in the red box is your actual formula for gravitational force. So force is equal to gravitational constant into mass of the two objects divided by square of the distance of separation between the two objects. Alright, so that's how we reach this equation, and G is the constant of proportionality. Alright, so we have we have a whole page of trivia here. Alright, so and here we have the value of G. So I just told you that proportionality constant is the set number. That value for capital G, which also happens to be the gravitational constant, is 6.673 times 10 to the power negative 11 Newton meter squared by kg squared. Alright, that is the gravitational constant. Alright, and how did you come up with this unit, you may ask me? If F is equal to gm by d squared, what is G equal to? If we make G the subject, that is if we isolate G to one side of the equation, G would be, D can go this side and it's going to get multiplied with F. So G is equal to F d squared by m. And this will go, and this will go here. Alright, so G, when we make G the subject, this is what it's going to be. And when we add the units, what's the unit of force? Newton. What's the unit of distance? Meters. What's the unit of distance? Squared. Meters squared. What is the unit of mass times the unit of mass? Kg into kg, which happens to be kg squared. Right? So that is how the units for gravitational constant. So I'm just going to say G, capital G units, Newton meter square per kg square, and I'm adding a power negative 2 instead of writing the kg square below the Newton meters. Alright, so that is how the units of Newton meters, the units of the gravitational constant came to be Newton meter square per kg square, and the actual value for it would be 6.673 times 10 to the power negative 11. Alright, so this is 7, not 1, don't get confused. Alright, okay, so that is the actual value of G. Alright, so we have an example here that I want you to close the solution. Alright, close it with the book, make sure you don't see it, make sure you cannot see it even if you are tempted to see it. Try to work it out on your own, because we just went through the formula and this is like a direct application of that formula. You just have to convert into different units which also you have practiced with, right? So I want you to hide the solution, make sure to go over this question, try to solve it to your best ability. Once you solve it, I want you to look at the answer and see if you got it right or wrong. And I want you to look through the solution regardless of whether you got it right or wrong, because if you got it wrong, you have to look at it anyway, and if you got it right, I want you to look at the solution and see if there is a better way of doing it. If the textbook did it the same way that you did it, awesome, good job. But if they did it in a different way, that will help you, that could possibly help you solve faster. That's what you need to do. Alright, you need to go work smarter, not harder, right? I mean, also work hard, but in the exam you need to work smart and go for easier ways to solve questions that would take less time, because in competitive exams like NTSE, NEET and JEE, time is your enemy. Alright, that is all I can say. Time is your enemy. If you do not control it, if you don't control how long you're taking for each question, you will not be able to finish your exam on time. Alright, so we have 2 questions here that I want you to solve, try on your own, answer on your own. If you are unable to answer a question, go back to that part of the video where I explain that concept, and make sure you write down your notes once you understand that concept. Alright, so what's the importance of the universal law of gravitation other than it being included in the syllabus? Alright, so the first one is that it binds us to the earth, or else we're all going to be flying off under zero gravity. So you know how zero gravity is, right? In spaceships or in outer space. If you've ever seen astronauts, videos of astronauts, they're floating. They're just floating. They're not able to stay in one place. Even in spaceships, they have these bars that are attached to the spaceship. That's my best attempt at drawing the spaceship. Yeah, it looks very bad. Okay, so there are bars that are attached to the spaceship that the astronauts tuck their legs or hands into that prevent them from drifting away, right? So gravitation binds us to the earth, or else we would be floating like the astronauts in outer space. So how else is gravity important? The motion of the moon around the earth, or else the moon would um, would have collided with the earth long ago when earth and moon started revolving around. I mean, when the moon started revolving around the earth, it would have fallen right then. It wouldn't have stayed this long if not for gravity, right? The motion of planets around the sun, just like how the moon would have fallen into the earth and collided with it, all the planets would have collided into the sun if not for gravity. And the tides due to the moon and the sun, because of the gravity, because of the gravitational force, the tides go higher when the moon is closer to the earth, and they are lower when the moon is farther away from the earth, right? So with that, we finished and like the primary part of gravitation, and now we have free fall. All right. So we have an activity here that you can try on your own. So we learned that the earth attracts objects towards it, and this is done due to the gravitational force. That is what we learned until now. Whenever objects fall towards the earth under this force alone, we can say that the objects are in free fall. So if there is an external force that is pushing the object down, that is not free fall. When the object is falling directly under the influence of the gravitational force and just under the influence of gravitational force, we can say that the object is undergoing free fall, or the object is in free fall. All right. So we know that an object experiences acceleration during free fall. So one way to think about it, if you've ever watched animations when you were young, so many animations, they have this concept that character jumps from a swimming pool. They like if this is the diving board for a swimming pool, let's say, and this is the pool itself. If they jump too hard, they shoot upwards, right? And when they're shooting upwards, they show it in a slow motion, like they show the character going up slowly, and then even when they're falling down, they start slow and then they keep gaining acceleration and they fall into the pool or into the water with a very great force. That was not the force with which they fell into the water is not the force with which they started falling down in the first place. As they continued falling down, they gained that acceleration, right? That's what um, these cartoons have been trying to tell us all along, right? That freely falling bodies accumulate acceleration and they experience acceleration during free fall. All right. So this acceleration is independent of its mass, whether it's a very heavy cartoon character or a very light cartoon character. It doesn't matter. What matters is that the object experiences acceleration during free fall. All right. So all objects, whether they're hollow, whether they're solid, big or small, they all fall at the same rate. All right. So this is a story that Galileo dropped different objects from the top of the Leaning Tower of Pisa in Italy to prove the same. So he dropped, apparently he dropped a metal ball and a feather, and he showed that both of them fell to the ground at the same time, right? So why is that? Because freely falling bodies accumulate the same acceleration as they fall, right? Now there is no I mean, it would have been controversial if you had the effect of wind, right? The wind is more likely to blow away that feather than the metal ball, but they said, but the clause is that an object, right here, it says that an object, whenever objects fall towards the earth under this force alone, there is no effect of the wind here. Alright, you should not consider the effect of the wind. It's just under gravity that you're trying to measure it. Then, regardless of the mass or the whatever the object constitutes, they should they should fall to the ground at the same rate. Alright, so G, that's smaller, like lowercase g, is constant near the earth. All the equations for the uniformly accelerated motions become valid by replacing A by G, right? So we learned the equations of motion in chapter 8, right? V is equal to U plus AT, S is equal to UT plus half AT squared, V squared is equal to U squared plus 2AS, right? So we just replace all the A's with G's. So V is equal to U plus GT, S is equal to UT plus half GT squared, V square is equal to U square plus half and plus 2GS. Alright, so these are the equations of motion for freely falling bodies, which are purely based under the influence of gravity. Alright, so we have another example and two more examples here, 10.2 and 10.3, and we have two questions that I want you to try on your own. I want you to try all 4 questions. The 2 questions are the 2 numericals. I want you to try on your own. Alright, and now we are talking about mass, right? So we've learned in the previous chapter that the mass of an object is the measure of its inertia, right? So I underlined that particular statement that said mass is the measure of inertia. If you didn't watch the previous video, go back and watch it so that you have this sense of progress, right? That you're moving orderly, right? So if you didn't watch the previous videos, feel free to start from the beginning. So that will help you know better. That will give you that sense of satisfaction that I watched all the videos until now, so I know everything that she's talking about, right? Or else we will have our own inside jokes. Those of y'all who were with us from the beginning, we'll have our own inside jokes, and those of you who just joined this video you'll feel left out, right? So I like this statement. I'm going to use it in all in the rest of the videos. I like it. Alright, so we learned that mass is the measure of inertia, and we also learned that the greater the mass, the greater is the inertia. So we learned that a truck has more inertia than a car, right? So the mass of an object is constant, and it does not change from place to place, whether it's on the earth or on the moon or even in outer space. The mass doesn't change, the mass is constant, but what changes is the weight. Alright, and weight is what we're going to talk about next. So we know that the earth attracts every object with a certain force, and that force depends on the mass because F is equal to Gmm. So depending on the mass, the force that is exerted on the object varies, right? So the force is dependent on the mass of the object and the acceleration due to gravity. Acceleration due to gravity is the lowercase g that we replaced A with in the equations of motion, right? And for the earth, this is like a side note. For the earth, g is 9.8 newton. Alright, so yeah, so 9.8, that is for the earth. Alright, that is the acceleration due to gravity. And acceleration due to gravity on the earth. Alright, so that's 9.8, and F is equal to ma. That's what we learned in the previous chapter. And when we were and since we were able to replace all the A's with lowercase g's, we can also say F is equal to m times g. That is the force that is exerted is the product of the mass of the object plus its acceleration due to gravity. Alright, and as the weight of an object is the force with which it is attracted towards the earth, the SI unit of weight is same as that of the force, which is Newton. Alright, because we're essentially measuring how much force is being acted upon an object. Alright, so as the weight of an object, so it's like this chain. It's like this chain. F equals ma, and since we were able to replace all a's with g's, we can also say F is equal to mg. And since weight is essentially just measuring the force, we can say weight is the product of the weight of an object is the product of its mass and the acceleration due to gravity. Alright, so g is constant at a given place. So at a given place, the weight of an object is directly proportional to the mass. Alright, so if you took one point on the earth and if you measure like 100 different objects, the force that is acting on the object, or which is the weight of the object, it is directly proportional to the mass, because g is constant at this point, right? G has a constant value no matter what the mass of the object is at this point. At a different point here, g will vary. So at a given point, the weight of an object is directly proportional to its mass. Alright, so we can use the weight of an object as a measure of its mass, and the mass of an object remains the same everywhere. Alright, so if we want to think of the situation in I'm sorry, my mind went blank. If we're thinking about a situation about planets, we could say the actual equation would be F equals g m, or I want to say g m1 m2 because I don't like saying mm. Alright, g m1 m2 by d squared. So F can be replaced with W because it's the weight. G will remain G. M1, M2 by, instead of D square, we're calculating the radius of that body, because whether it's a star or an asteroid or a planet or a moon or the moon, right? It doesn't matter. It's just that we're finding the force that a celestial body exerts on an object that is present on the surface of that. So if this is the center and if the object is here, we are trying to measure the distance between the center and the object, which happens to be the radius of the body. So by r squared. Alright. So that is the equation for celestial bodies, to find out the force that is being exerted by a celestial body onto an object that is present on the surface of the celestial body. Alright. So if we apply that to the case of the Earth's moon, and I'm making sure that I say the Earth's moon because there are many moons. Jupiter has 4 moons, right? So I'm going to say the Earth's moon, right? So they gave us the mass of the moon, which happens to be 7.36 times 10 to the power 22 kgs, which is a lot. Alright, and the radius of the moon, which is 1.74 into 10 power 6 meters square, because we're doing r square. So the whole radius is being squared, and so weight would come out to be this number times the gravitational constant times the mass of the object, and that is equal to, if you want to represent it in scientific notation, this would be the answer for that. So this is 10.18a and this is 10.18b. We are dividing 10.18a by 10.18b. So this is the first equation, this is the second equation. So 1 by 2, that's how we write it in math, right? 1 by 2, that would be 0.165 or 1/6. So this is the weight on the moon, and this is the weight on the earth, not scientific notation. This is the moon and this is the earth. So moon, the weight of an object on the moon divided by the weight of an object on the earth would be 1/6. Alright, so the weight of the object on the moon is 1/6 of its weight on the earth. So if you weigh let's say 36 kilograms on the earth, you are going to weigh 6 kilograms on the moon. Alright, so here we have an example. The mass of an object is 10 kgs. What is its weight on the earth? So mass is 10 kg and acceleration due to gravity would be 9.8 meters per second square. I just realized I mentioned that G was 9.8 Newton previously in the video. I'm sorry about that, I got confused. It's meters per second square. Alright, so weight would be mg. I don't want to make you guys twist your necks. So mass would be 10 kg. Mass would be 10 kg. Acceleration due to gravity would be 9.8 meters per second square. So weight would be mg, which is 10 kgs into 9.8 meters per second square, which is 98 newton, or 98 kg meter per second square, and kgs meter per second square is newton. Alright, that's how you solve this question. And I want you to try the same for, I want you to try it on your own for example 10.5 and the two questions. Alright, and the two questions, two questions here. And now we're moving on to thrust and pressure. Alright, so why can a camel run in the desert easily? Like, the desert is full of sand and we can barely walk our normal pace in that sand. How come a camel can run, right? And why does an army tank that weighs more than 1,000 tons rest upon a continuous chain? And why does a truck or a motorboat or a motor bus have such wide tires? Why do the cutting tools have sharp edges? So why are knives sharp, right? So all these questions, I'm sure most of us had most of these questions, right? So to understand that, we have thrust and pressure to thank, right? Because they helped us understand the reasons behind these questions. Alright, so thrust and pressure. So thrust is the net force in a particular direction. Thrust is the net force. Why do I keep doing this? Yeah. The net force in a particular direction is thrust, and the force per unit area is pressure. Alright. So the net force, that means the complete total force in a particular direction, east, west, north, south, all the other directions, right? The total force that is being applied in a particular direction would be thrust, and the force per unit area would be pressure. Alright, so let's say you have this bulletin board and you want to put up a group chart, let's say. Alright, that the following students belong to this house, this other house. You know, we have different schools of different houses, right? There's schools that have names of scientists as their houses. There are names of precious stones. There are flowers and freedom fighters, all of that, right? So if you say, suppose we take scientists and we say Aryabhatta, right? Bhaskara, and you want to name few people here and a few people there and a few people in two other houses, then you want to put up that chart in your classroom or outside your classroom, and you have a bulletin board. You wish to put it up on that. So what do you use? Do you use tape? You don't use tape, right? Because it won't stand. Tape will not work on a bulletin board. If you're think of like a an actual bulletin board with that blue or green surface, and it goes through when you use a pin, you use that pin, right? So tape doesn't work on that. You can't use magnets on that. You can't use knives on that. I mean, technically you can, but you don't. You use a pointy, I keep doing, you use a pointy needle, and you have a pin that's like that, right? And you use that to push it. This is the pin, right? This is the needle, and it's sharp, and it goes through the bulletin board, and it keeps that paper in place. Why do you do that? First of all, why do you use this pin? And second of all, when you're pushing this pin into the bulletin board, if you can imagine yourself doing that, which finger do you use to push it in? Most of you might have imagined yourselves doing it with your thumb. Why is that? Because it's easier to do it with your thumb, because the surface area of your thumb is greater than the rest of your finger's surface area, right? So when you apply a force on the surface area of the head of the pin, the force is directly perpendicular to the surface area. If you have your index finger, you're essentially just pushing it at this point here. If you use your index finger, you're pushing it at this point. But if you use your thumb, you're pushing it on this thing, on this side, which is right, and this is wrong. Alright, so you use your thumb because it's directly proportional to the surface area of the board, and the force acts on a smaller area at the tip of the pin, right? This is smaller area as compared to this being a larger area. So the force that you are exerting on this larger area is being acted upon by the bulletin board on the smaller surface area. Alright, so that is one situation in which you use a smaller surface area to fix a chart or something on a bulletin board. Alright, and you're using your thumb to press the side of the pin with a larger surface area, and that is when that force is being applied perpendicular to the board. Alright, so you have situation 2 that I want you to read, try it if you can, and understand the difference, right? So the effect that you saw in both situations is that if the pressure was being acted upon a larger surface area, the pressure that you needed to put was less than that you would have needed to put if you used force on the smaller surface area side. Alright, so this sentence might have sounded complicated, so let me break it down for you. If you go back to the pin situation, think about it. If you used your thumb to press on the side of the pin with a broader surface area, the back of the pin, not the needle, you would have need less pressure to push the pin inside, right? Suppose you use the other side of it. First of all, it would take a very long time for that large surface area to go inside the bulletin board, and in managing to push that large surface area into the bulletin board, you would find that the needle, the front end of the pin, went into your finger, but the pin didn't go into the bulletin board, right? So why does that happen? Because the pressure increases if you decrease the surface area. Alright, so pressure is inversely proportional to area. Alright, and pressure is directly proportional to the thrust. Alright, so the pressure is directly proportional to the amount of force that you applied towards a particular direction. Alright, so directly proportional to TH TARUST. Alright, so pressure is inversely proportional to area or surface area, I can say, and it's directly proportional to the thrust. So just like how we did it for the force of gravitation, we can say that if this is equation 1 and this is equation 2, then we can conclude that pressure is equal to thrust per unit area, or thrust by area, or thrust by surface area. Alright, that is your formula for pressure. Alright. Okay. So let me get rid of this because I'm covering the material. Okay. So substituting the SI unit of thrust in area. For thrust it is the force per unit area. Thrust is the force, so it will be Newton, and surface area is meter square. So Newton per meter square is Pascal. Alright. So there are a few numericals here. I think it's one. Yeah, but it's a very important model of numericals that you can expect in NTSE and CBSE boards. Alright. And once in a while in NEET and JEE, but they probably won't ask such basic questions. It's going to be your luck if they do. Alright, so now that we talked about pressure and thrust, I want you to go over this numerical, see if you can solve it by yourself. If you cannot solve it by yourself, go back, rewind, and start watching from the beginning of the concept, thrust and pressure. Start watching from there, take your own notes, make sure you understand, come back and solve it, and then go through the solution. Alright? So now we're talking about pressure in fluids. Alright, but we have a statement here that says the same force acting on a smaller area exerts a larger pressure and a smaller pressure on a larger area. Alright, so that's essentially what I just said with the pin example. So if you apply X amount of pressure, it would the surface areas of those two objects would make it seem like two different things. If it has a greater surface area, you would need to apply less pressure. If it had a lesser surface area, you would need to apply more pressure. Alright, so this is like a basic relation between surface area and pressure. First of all, the fact that surface area and pressure are inversely proportional to each other should make it pretty intuitive for you, but even if not, that relation is a very handy relation that you can note down and keep revising. Alright, so that is the reason behind a nail having a pointed tip and a knife being sharp edged and a building having wide foundations. If a building was standing on like just two pillars, and if the structure was like this big, it wouldn't be as stable as it would if there was multiple pillars, right? Because the foundation should be wide and the foundation should be wide and it should be able to support that bulk of the building on its pillars. Alright, so we're talking about pressure in fluids. So fluids doesn't necessarily mean just liquids. Alright, liquids and gases are fluids because they flow, right? They have fluidity. Liquids and gases have fluidity. That's why they're called fluids. Alright, a solid exerts pressure on a surface due to its weight. And fluids also have weight, right? You say, if you carry a water bottle, you would say, oh, this is heavy. Why is that? If it was an empty bottle, it wouldn't have been as heavy. How come it became so so heavy once the bottle was full of water or a liquid? How come that happened? Fluids also have weight, alright? So, similarly, if you have I don't mean to just limit myself to liquids, even for gases, if you have a water bottle that has complete vacuum in it, it has no gases, no liquids, no solids, nothing, it's just vacuum, that would weigh lighter than the bottle which has just gas. It doesn't have water, it doesn't have a liquid, it has a gas, right? But the bottle which has vacuum in it, which vacuum is neither a gas, nor liquid, nor solid, nor plasma, nor Bose-Einstein condensate, right? First chapter of physics, of chemistry, right? That is vacuum. So the bottle which has vacuum would obviously be lighter than the bottle which is full of air or some gas, right? That shows us that fluids have weight. Whether it's a gas or a liquid is irrelevant. Granted, gases are lighter than liquids, but gases also have weight. Gases also have mass. That's why fluids also have weight. And because of that weight, they exert pressure on the base of the container and the walls of the container in which they're enclosed, and the pressure exerted in any confined mass of fluid is transmitted undiminished in all directions. Alright, so it's not being transferred to any other place for it to decrease. Alright, it's being transmitted undiminished in all directions. Alright, so now we're talking about buoyancy. Alright, have you ever had a swim in a pool and felt lighter? Have you ever drawn water from a well and felt that the bucket of water is heavier when it was out of the water than when it is inside? Right, that happens. Even when you're bathing, if you put the mug inside the water, inside the tub or bucket of water, and you're lifting it to the surface of the water, it would be lighter than once you remove that mug out of the water and into the air, right? So it's the same concept, buoyancy. Alright? And have you ever wondered, this is a very common question, why does a ship that is made of iron and steel not sink in water, but the same amount of iron and steel in the form of a sheet sinks? So this is a very important give reason question or explain question, right? They can be answered by taking buoyancy in consideration. So we have an activity here that you can try that would help you understand buoyancy by observing it firsthand. Alright, so the force due to the gravitational attraction of the earth acts on the bottle in downward direction. Okay, so this always keeps happening. Alright, I keep selecting the eraser instead of a pen, and I keep drawing with the eraser, and you guys can't see. Alright, so this is a beaker and it has water. Alright, this is all water, and this is an object. I'm gonna say it's half submerged and half floating, and I'm going to say it's a block of wood. Alright, so on this block of wood, there are many forces that are acting. To start, first of all, is a force acting in the downward direction, that is the gravitational attraction, acceleration due to gravity. Alright, that is in the downward direction. So the bottle is being pulled downward, but the water exerts an upward force on the bottle or on the block of wood. So as acceleration due to as the gravitational force is pulling the block of wood downward, the force by water is acting upwards on that block of wood. So weight of an object is the force due to gravitational attraction, right? So when the block of wood is immersed, the upward force exerted by the water on the bottle is greater than its weight, right? So it rises up when the block of wood is released. To keep the block of wood, I'm going to switch to bottle because it keeps saying bottle everywhere. So to keep the bottle completely immersed, the upward force of the bottle due to water must be balanced. Alright, so once you release it, the bottle is going to spring upwards or is going to fall downwards. To keep it balanced, the two forces must be equal but opposite to each other, right? So how will they be equal to each other when we clearly saw that they were different values? It has to be another force has to be acted upon the object. Alright, so I'm going to scroll downwards. I'm going to scroll down. Too much physics. Alright, so they're definitely, so gravity and the force by water, they're both definitely not equal to each other, because the bottle is either sinking or it's floating. So there must be another force that will balance the force by water and the gravity, and that is buoyancy. Alright, so whether a given object sinks in water, floats on water, or stays partially submerged under water is dependent on the value of the buoyancy, the numerical value or the magnitude of the buoyancy, and the direction in which it's acting. Alright, so once you understand that, we can ask ourselves, why do objects float or sink when they're placed on the surface of water? Not water on the surface of any fluid for that matter, but let's talk about water because it's easy for us to experiment on. We have an activity in which you need to take a wood piece of cork and a nail, drop them both in water. The cork floats, the nail sinks, right? This is sink, this is float. Why do the objects either float or sink? If they're floating, how come they're floating? And if they're sinking, how come they're sinking? That's the question that we're supposed to ask ourselves. So the reason behind the nail sinking is that the gravitational force of attraction that acted on the nail was greater than, I'm just going to represent the gravitational force by small g and the force by water by F sub W, alright? So for the nail, let me do color coding here. So we're talking about the cork in green color and about the nail in blue color, alright? So why did the nail sink? The nail sank because the attraction by gravity was greater than the force that was exerted by the water. So F sub W represents the force acted upon by the water. And why did the piece of cork float? Because the force of gravity is less than the magnitude of the force of gravity was less than the force exerted by water. So if you think of it like a tug of war, and if the two sides, one side is gravity, one side is the force exerted by water, because the force exerted by gravity is more, the nail sank, right? If this is more, the nail went, because gravity is more, the nail went towards gravity. If the force exerted by water was more, the nail would have gone towards the surface of the water, but that didn't happen. Gravity was greater than the force exerted by water, so the nail sank, and because gravity was less than the force exerted by water, the piece of cork was floating. Alright, so that's an easy and fun way of remembering it, and I'm sure you will remember it easily because it's just understanding the concept behind a game which we already know. Alright, so here we have another exam activity, right? And this is what I just said. And why did it happen is because of the difference in their density. Density, we know, is mass per unit volume, and the density of cork is less than the density of water. Alright, so I was representing nail with blue color, so the density of nail is greater than the density of water, so it sank. Alright, however, the density of cork was less than the density of water, so it was float. Alright, so we saw that the object cork was floating. Alright, so the density of an iron nail is more than the density of water, that's why the nail sank. Alright, to answer the question that we previously asked, why does an iron nail sink but an iron ship why does an iron ship float on water but an iron sheet sink? Because the density is different. So for ships we have hollow space inside, right? When we have hollow space inside, the mass per unit volume is less. So the density of a boat or an iron ship is less than the density of water, but the density of an iron sheet is more than the density of water, which is why an iron ship floats while an iron sheet sinks in water. Alright, we have 3 questions here that I want you to try on your own, and now it's time to talk about the Archimedes principle. Alright, just a moment. Alright, I need to go to that one. Okay, so Archimedes principle, let's take it. So when we perform an activity 10.7, you will observe a few things. That's what we're going to talk about now. Activity 10.7. Alright, so you'll find that the elongation of the string or the reading of the balance decreases as the stone is gradually lowered in the water, right? So no further change is observed once the stone is fully immersed in the water, right? So what do you infer from the decrease in the extension of the string or the reading of the spring balance? We know that the elongation produced in the string or the spring balance is due to the weight of the stone, right? So it is because of the weight of the stone that we saw the string being elongated, and we saw the reading of the water increasing. That is because of the weight of the stone. And once the stone was fully immersed, there is no more weight that is being added on into the water, so the reading stops, and the elongation of the string also stops. Alright, so the net force on the string decreases and elongation also decreases. Right, the upward force exerted by water is known as the force of buoyancy. Alright, so buoyancy is always exerted upwards. That is one thing you need to remember. Buoyancy is always exerted upwards, whether buoyancy is dominating the force of gravity or the force of gravity is dominating buoyancy is what determines whether an object is going to sink or float. Alright, so since the extension decreases once the stone is lowered in water, completely lowered, it means that some force acts on the stone in upward direction. What is that? As buoyancy. As a result of that force, the net force on the string decreases and elongation also decreases. Alright, so the magnitude of buoyant force experienced by a body, what is that? Is it the same in all fluids for a given body? Do all bodies in a given fluid experience the same buoyant force? The answer to all these questions is contained in the Archimedes principle. Alright, so what is Archimedes principle? It says when a body is immersed fully or partially in a fluid, it experiences an upward force that is equal to the weight of the fluid displaced by it. Alright, so this is a little confusing. I found it confusing when I was doing NCERT 9. So when a body is immersed fully or partially in a fluid, so it doesn't essentially need to be completely immersed. The stone could have been partially immersed, it could have been half immersed or 3/4 or 1/4, it doesn't matter. It experiences an upward force. What is that upward force? Buoyancy. And how much buoyancy does it experience? It experiences the force that is equal to the weight of the fluid displaced by it. What is it? The part of the immersed object, the part of the immersed body. So the immersed part of the body displaces a little fluid, and that fluid, if you measure the weight of the fluid that is displaced by the immersed part of the object, regardless of whether the object is completely or partially immersed, that weight will be equal to the buoyant force that is acting upon that immersed object. Alright, so now can you explain why a further decrease in the elongation of the string was not observed as the stone was fully immersed in water? Yes, you can, right? When the stone is fully immersed in water, there is no more chance for the stone to displace more weight. And when there is no more weight, there is no more buoyancy acting on the stone. And because there is no more upward force acting on the stone, there is no decrease in the elongation of the string. Alright, simple answer, simple concept. If you pay attention, if you are able to understand all the concepts, it's going to be very easy for you. Alright, so this is a trivia thing here for you. It's fun. We had I think we had a lesson about this in English in 6th grade. I'm not sure. Alright, so Archimedes' principle has many applications. It's used in designing ships and submarines. Alright, so it is because of Archimedes' principle, the application of Archimedes' principle, that iron ships are able to float on water, that wooden ships are able to float on water. Alright, and lactometers, which are used to determine the purity of sample of milk, and hydrometers that are used to determine the density of liquids, are all based on Archimedes' principle. Alright, so now you have some questions, 2 questions that I want you to try on your own. And now we are going to talk about relative density. Alright, so density we know is mass per unit volume. What is relative density? Right, relative density is the density of a substance by density of water, and there is a clause here at 4 degrees Celsius. That is because at 4 degrees Celsius, density of water is the greatest. Alright, this is not mentioned in your textbook, but it is handy for competitive exams, and even for CBSE exams. It doesn't hurt to say at 4 degrees Celsius, it's just 2 extra words. Alright, and that will impress your teacher, and that will let the teacher know that you actually know what you're writing in your exam. Alright, so since the relative density is a ratio of similar quantities, it has no unit. How is that? Density of a substance is mass per unit volume, so it could be grams per centimeter cube or kilograms per meter cube, it doesn't matter. I'm just going to go with grams per centimeter cube. That is the density of a substance, x grams per centimeter cube. Density of water is y grams per centimeter cube, let's say. Alright, so grams per centimeter cube get cancelled, and this is a ratio that remains, which is why relative density has no units. It's just a plain, simple number. Alright, that's why we say here relative density of silver is 10.8. That's it. We are not saying 10.8 grams per meter cube or 10.8 kilograms per centimeter cube, nothing. Alright, it's just a number. It's a straight, simple number. Alright, so one thing I want to mention is that in such questions, they give you the relative density, they give the density of water, and they ask us to find the density of that substance. Alright, so when they give the density of water in kg per meter cube, you need to give the density of that object, in this case it's silver, in kg per meter cube, or here they asked in SI unit, so you need to give in kg per meter cube. If they asked in CGS unit, you need to give in grams per centimeter cube. Alright, so the difference between SI unit and CGS unit is that SI unit is an international system, so it's French for System International, and that's an international system. So in every all across the world, if you consider SI units, you will talk about the same unit. In CGS units, we're talking about centimeters, grams, and seconds. So it's length, mass, time. Alright. There was also the FTS system, that is foot, pound, second. So if you think about it, this is what we use in India, and this is what is used in America. That's like, they're not the only countries that use it, but if you're familiar with, if you're more familiar with just these 2 countries, this is like a basic difference. The CGS system is commonly used in India, and the FTS system is commonly used in America. Alright, seconds that measures time. Alright. So we use CGS system. So if they ask what is the density of silver in CGS units, you're supposed to say, you're supposed to express your answer in grams per centimeter cube. Alright. And with that, we finish the lesson. Yay! Right? So we have what you've learned points here that you can, that's just the whole chapter in a few points. You can go over them a day before your exam or the night before your exam or the day of your exam, right? Okay, so we have a few exercises that I want you to try once you are sure that you are confident in this chapter, alright? If you are not, feel free to replay the video or go back to those parts which you didn't understand or you had you understood a little but you want a little more clarity. Go back and play it again and try to understand. Take your own notes, right? And once you are sure that once you're confident that you know this chapter very well, come back to solve the exercises. Alright. So now we have points to recap. Okay. So points to recap. First, we started with the introduction of the lesson. We talked about what gravity actually is. We talked about the applications. We talked about how we asked ourselves a few questions. I can say, how come the moon does not collide with the Earth if it's always moving around? How come the apple fell to the ground when Newton was sitting under the apple tree? Stuff like that. We asked a few questions and we introduced gravity. And then we talked about the universal law of gravitation along with applications, right? We talked about free fall. We talked about how since the time we were watching animations, we have seen how objects that undergo free fall only have acceleration as they fall to the ground. We talked about mass and weight. Alright, we said mass is constant, but weight varies based on the position, right? We also introduced a new concept called acceleration due to gravity, which is represented by lowercase g, that is 9.8 meters per second square, right? Then we talked about thrust and pressure, and in pressure we talked about pressure in fluids, buoyancy, how do we determine whether an object is going to float or sink. That's what we learned. And then we learned about Archimedes' principle, right? We learned about relative density and how relative density has no units, right? And then I just scroll through the exercises pages, and that is how we end this chapter. Alright, so thank you so much for watching this video. I hope you understood the concept better, and feel free to head on to the next video, which is also a physics chapter, I believe, I'm not sure. And don't forget that you can do this. Alright, have a great rest of your day. Don't forget to like and share this video, subscribe to our channel for more content, and you can do this. All the very best. Rock your exam. Alright, bye bye.